Today we're going to look at a few more examples of finding the interval of convergence for a power series. And we've talked about the different factors that can show up in the coefficients and how those factors affect the radius of convergence. At the bottom, we've got the polynomial and radical factors, or the rational factors, and that's just going to affect the endpoints. When we plug in the endpoints that we get from the ratio test, when we plug in those endpoints, we're looking at the points that the ratio test is blind to. So that's when the polynomial and the radical stuff will come into play. And we're just trying to determine if those endpoints should be included or not included. As far as expanding any finite radius of convergence, we have the exponential factors. And what we should be thinking about there is we just gather up all the exponential factors, and that's like the common ratio of a geometric series. So here in the exponential factor department, we're thinking common ratio. Even though we might not be looking at a geometric series, we should think common ratio of a geometric series. And we know that the common ratio needs to be strictly less than 1 for a geometric series to converge. So it's the exponential factors that's going to expand or contract a finite radius of convergence. The other possibility is that a power series only converges at the center with a 0 radius of convergence, or it converges for all real numbers with an infinite radius of convergence. For that to happen, we need to see some factorial factors, because the limit from the ratio test, in the limit from the ratio test, the factorial factors are the ones that are going to leave n behind. That's probably that's a very sloppy way of thinking about it, but it's the way that it comes out in my mind. So only factorial factors leave extra n's, an imbalance of n in the limit from the ratio test. With the polynomial and radical factors, the n's will always be balanced in the ratio test. So the limit from the ratio test will always be 1. So the limit from the ratio test is 1 with these factors. These factors. The limit from the ratio test is always 1 with these factors. The n's are balanced. Oops, not numerator, numerator to denominator. But with factorial factors, we'll leave an n behind in the numerator or denominator. So the factorial factors are going to leave an n behind in the numerator or the denominator. If we, as an example, if an is the square root of n plus 1, then an plus 1, this is kind of a bad choice. I'm going to make it an plus 12. Then an plus 1 is the square root of n plus 1 plus 12, or the square root of n plus 13. Now, when we look at the limit as n goes to infinity of this ratio, we've got an n to the 1/2 over another n to the 1/2. The powers of n are balanced. So in this scenario, the powers of n are balanced. Numerator and denominator. But if, for example, we have a factorial if an is a 2n factorial, then an plus 1 is 2 times n plus 1 factorial, or 2n plus 2 factorial. So now, the limit from the ratio test, the n's will be out of balance numerator to denominator. So we don't get that interval, 1, the limit of 1. So here we'll have a limit as n goes to infinity of an plus 1 over 2n factorial, or an. Now, if I simplify the larger factorial until I get to the smaller factorial, the larger factorial is 2n plus 2 times 2n plus 1, and then we get to the smaller factorial, so I can stop, 2n factorial. So the 2n factorial cancels out, and what's left behind is 2n plus 1 times 2n plus 2. So what happens is that with factorial factors, we leave n's behind in the numerator as we cancel out the 2n factorial. So in the limit from the ratio test, the powers of n are out of balance because of the factorials. We've got an n squared in the numerator and a constant in the denominator, and n to the 0 in the denominator. That's out of balance. With the radical that we had before, we had an n to the 1/2 in the numerator and an n to the 1/2 in the denominator, and the ratio test just ignores that. So with this in mind, we can leverage these observations and just break down each of the factors in the coefficients of a power series and figure out what's going on. So let's look at an example. So for example, let's suppose we have a power series and we'll go from 0 to infinity. We'll have, let's say, 3 to the n times x minus 1 to the n over 5 to the n times n squared. Now let's just grab all the pieces that we can identify. Just grab all the pieces that we can identify. So we've got x minus 1 to the n. That tells us that the center is going to be at 1. I've got a 3 to the n in the numerator. That's going to give us a 1/3 for a radius, but a 5 to the n in the denominator is going to give us a 5 for the radius. So it looks like the radius is going to be 5/3. This n squared is in the denominator. So on one end, my power series is on one end of the radius of, on one end of the interval of convergence, my power series will look like a minus 1 to the n over n squared, which converges. And on the other end, of the interval of convergence, the power series will look like 1 over n squared, which also converges. So it looks like both endpoints are going to be included. So to me, it looks like my interval of convergence is going to be the absolute value of x minus 1 is less than or equal to my radius 5/3. I can use an absolute value inequality because it looks to me like both endpoints are included.
Professor, how
Yeah,
come it's 5/3 instead of 3/5?
because we're not just looking at what's going on here, we're thinking about the common ratio of the geometric series. So if I just grab the exponential factors, if I ignore the n squared for now, if I just grab the exponential factors and we think of geometric series, a geometric series converges if the common ratio is less than 1. A geometric series converges if the absolute value of the common ratio is less than 1. And if we ignore the n squared part and think about just a geometric series that had a 3 to the n over 5 to the n times x minus 1 to the n, then we're looking at the common ratio is 3 to the n times x minus 1 to the n over 5 to the n, and this all has to be less than 1. If I solve this for the oops, I don't need the n's with the common ratio. My common ratio will be 3 times x minus 1 over 5. And if I solve this for the absolute value of x minus 1, I have to divide by the 3 and multiply by 5.
Got it. Okay, thank you.
And then the n squared tells us that both endpoints are included. One end looks like, so one endpoint will look like the series minus 1 to the n over n squared, which is absolutely convergent. And the other endpoint will look like the series 1 over n squared, which is, well, absolutely convergent, oops, which we saw in the previous one. So if we start moving things around, we can start making adjustments. We can see how things change if we start making changes. So if I keep my x minus 1 to the n, if I have a 5 to the n down here, right now we're looking at it, it's going to be the middle is 1 and a radius of 5. And n squared down in the denominator gave us both endpoints. And then we'll have a 3 to the n up here. So the 3 to the n is going to make our radius a third, because that's contributing to the common ratio. But if I trade my n squared for a square root of n, now I have a different decision about the endpoints. Now one endpoint will look like an alternating 1 over a square root of n, and the other, which converges, and the other endpoint looks like a non-alternating 1 over square root of n, which diverges. So I've changed up the endpoint scenario. One endpoint will be minus 1 to the n over n, a square root of n, which is conditionally convergent. But the other endpoint is a square 1 over the square root of n, which diverges. So one endpoint is going to be included, and the other endpoint will not. I've still kept my center at 1 and my radius of 3/5. I no longer get to use an absolute value inequality because one endpoint is in, the other endpoint is out. So my base from the geometric series, this part hasn't changed. We don't technically have a geometric series. This is technically not a common ratio, but the basic interval of convergence, once again, I don't need the ends in my common ratio. The ends cancel because I'm doing a common ratio. I'm dividing the n plus first term by the nth term, which is why geometric series fits into the ratio test so well. But I still want the absolute value of x minus 1 to be less than 5/3. But from my radical part, I see one endpoint is included and the other endpoint is not. The endpoint that'll make things alternate is included, but the endpoint that just cancels out to 1 will not. So we'll have to make a note of where the endpoints are. In the middle is 1, and we have a radius of 5/3. So we'll have 1 and 5/3, which is a terrible way to write a fraction. Don't do that. Only do that in your mind. I'm just trying to review adding fractions because too often I see everybody just going right to improper fractions. I'm like, well, that's just so excessive. And it hides the fact that when we say something like 2 1/3, we're saying 2 plus 1/3, like literally 2 plus 1/3. But that's beside the point. 5/3 is 1 1/3, so we have, actually we should call this 2 2/3. Did I do that right? Who knows? And then over here on this end, we have 1 minus 5/3, 1 and a negative 5/3. So 1 minus 1 and 2/3 is going to be, let's see, the ones cancel out, and I'll have a negative 2/3. Let's see, 1 is 3, let's see, get rid of that. 1 is 3/3, so negative 2/3 plus 5/3 is 3/3. 3/3 plus 5/3 is 8/3, so we're good. So there are our endpoints. The negative 2/3 is going to, when we subtract the 1, that's going to give us the alternating side. This is going to give us the alternating side. So negative 2/3 is included. But the 2 2/3, when I multiply that by 3/5, I end up with a positive 1. So that's the diverging side. So here is my, I put or equal to. I specifically designed this to have a less than on that side. We don't get to use a compound inequality here because both endpoints are not included. We could still write this in terms of x minus 1 is strictly less than 5/3, but greater than or equal to negative 5/3. And then just add 1 all the way through. The point is that we want to be able to read what's going to happen without having to write the ratio test. Notice I haven't written any ratio test. I haven't written down limit as n goes to infinity of absolute value of an plus 1 over an and started to simplify things. It's better to know what's going to happen. It's better to just know that 17 times 3 is 51 and not have to write down 30/21. It's better just to know. If you find yourself in a situation where you have to write down the ratio test, then we should know how to do that. But it's better to not write things down. The point of being in a math class is to see enough and gain enough experience that you don't have to write things down all the time. That's why I 100% object to the show my calculations. So many teachers utilize the rules of not show your calculations, but show my calculations. Show me, copy the things that I had you write down. But you might not have to write down those steps. And rather than using the speed with which you can go through the problem in your mind, we force you to slow things down and write things down, which is counterproductive. Of course, those are on tests, and I object to tests anyway, so I guess there's other issues at play. Now, if I take this square root of n and push it up into the numerator, now all of a sudden, both endpoints are not going to be included. So if I have a sum as n goes from 0, oops, I should have changed this to a 1 because the square root of n is. Oh, now it's not going to matter. So now if I take that square root of n and put it up into the numerator, I can still think of, oh, I made myself things difficult on myself here. The geometric part of this, the geometric factors still make us think 3 times x minus 1 over 5 is the common ratio, and that requires that the absolute value of x minus 1 be strictly less than 5/3. So we've got the big part of our interval of convergence, and then, but when we look at this square root of n in the numerator, at one endpoint, we'll have an alternating square root of n, but this is an n to the 1/2. That diverges, and then the other endpoint also diverges. So neither endpoint is included. So it looks like our interval of convergence is just going to be this. X minus 1 has to be strictly less than 5/3. So once again, we want to be able to see what's going to happen and not just wonder what's going to happen and then try to follow our nose through some process. Right. So let's take a look at the change that I've made here. So in this case, we start looking at the geometric part and we see the common ratio is going to be the same as before. We should start thinking x minus 1 has to be, the absolute value of x minus 1 should be less than 5/3. But then we stop and we say, hang on, this one has a factorial in it. And it's got a factorial in the numerator and nothing to counter the factorial in the numerator factorial in the denominator. There's an n factorial in the numerator with no factorial in the denominator for balance. So what's going to happen is that now we ignore the 3/5 to make our radius 5/3. We're going to ignore this 5/3 radius business. This n factorial in the numerator with that nothing in the denominator means that the only way to get convergence here is to zero out all the terms. So this power series is only going to converge when x equals 1. That is, the radius is 0. This is the instinct that we want to build. This is not the what we might see. Let's run a ratio test to see this happen. Let's verify this with the ratio test. So we'll take the limits as n goes to infinity of the absolute value of this term plus 1. So 3 to the n plus 1 times n plus 1 factorial times x minus 1 to the n plus 1 over 5 to the n plus 1 divided by this term, 3 to the n times n factorial times x minus 1 to the n under 5 to the n. Let's cancel out all the corresponding parts. So 3 to the n plus 1 divided by 3 to the n is going to leave a 3 to the 1 behind. 5 to the n plus 1 will cancel out a 5 to the n, which will leave a 5 behind in the denominator. We cancel out the factorials by writing the larger factorial until we get to the smaller factorial. And we keep doing this until we can just see how things are going to cancel. So the n factorial cancels out, leaves an n plus 1 in the numerator. And then the x plus 1 to the n plus 1 cancels an x plus 1 to the n and leaves x minus 1. So the factorials have left behind an n plus 1 in the numerator. I'm supposed to say x minus 1. They've left the factorial left behind an n plus 1 in the numerator. And so my limit goes to infinity. Since infinity is never less than 1, we have to zero out all the terms. Infinity is never less than 1. So that's why we have to zero all the terms to get convergence. Any questions? All right. The next thing we need to consider, now that we've got an idea about how power series work, this is all about finding the interval of convergence for a power series. And the reason that we want to find the interval of convergence for a power series, if we think back all the way back to when we first started talking about chapter 9, we want to use power series as models for functions. The reason that we want to use power series as models for functions is that power series, if we stop writing them, just look like polynomials. And polynomials are pretty easy to deal with. So if instead of n going from 1 to infinity, if n just goes from 1 to 10, I've got a 10th degree polynomial. And then if that's not good enough for our whatever application we're working on, then we can just do more terms, 20 terms. And then we got a 20th degree polynomial. I don't know how important this is in an age where we have massive computing power, but where we have calculators and we have machines that have our transcendental functions on them, right? Sine, cosine, tangent. We got our natural logs, our exponentials. So I don't know how useful it is to replace, say, the function e to the x, which is such a well-known function, with the power series. But what the other thing that we can do with power series is that we can take a description of an unknown function and try to see which power series fits that description. Then either we'll recognize the power series or we'll recognize characteristics of the power series and be able to identify the function we're working with. Or at the very least, that power series can stand as an approximation of the solution, approximation of the function. And since it's a power series, if we need a better approximation, we just generate more terms. And in an age of massive amounts of computing power, that's pretty good. You have the function. You don't have a nice, clean, mathematically satisfying solution, but you have a solution that you can use to evaluate the function without knowing what the function is. And that's pretty dope. So the next thing we need to talk about is, where do power series come from? Students being awesomely pragmatic. One year I asked, so where do power series come from? And a student was like, oh, chapter 9. Way to focus. That's awesome, because I was like focusing on exactly the task that we're dealing with. Super pragmatic. I can dig that. But I took off half points because, they also show up in chapter 10. I'm just kidding. I took off all the points. I round off. I'm just kidding. That wasn't worth points. All right. So tomorrow we need to talk about where power series come from. We're going to talk about a particular type of power series that you're already familiar with. We've already started on the path of power series. You just didn't know it because we stopped at degree 1 instead of going to degree infinity. All right, that's going to do it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing.